Yeah, so now I'm recording. So anyway, thank you very much to be here, Vlatko. I know that you are a night bird, and it's not your usual time to be already at work. So thank you for being with us. And so let me remind so that you did your PhD in Imperial College quite some time ago, and now you are professor in quantum information at Oxford and professor of physics at National University of Singapore. So you know very well Singapore. You come very often here, and I have the pleasure also to meet you sometimes. So you have published over 350 research papers on various topics in quantum physics, quantum computing, and you are one of the Clarivate highly cited researcher. So I mean, to say that your research has a lot of impact, and you give a lot of plenary and you invited talks during your career. This includes specialized talks at the Solvay meeting in 2010. So I mean, everybody know about this Solvay meeting in early 20th century, of course. So this meeting are occurring every 5 years or 10 years. You know that? What is the time?
Yes, I think it's every. You're right. It's 4 or 5 years. Yes.
Okay.
Yeah.
And you give also a popular one at the International Safe Scientific in 2007. So you were awarded by the Royal Society Wolfson Research Merit Award in 2007, the World Scientific Medal and Prize in 2009, the Marco Yarrick Awards in 2010, and he was elected as a fellow of the Institute of Physics in 2017 and a member of the European Academy of Science in 2020. You have held many visiting professorships, among which the University of Vienna, Belo Horizonte, Perimeter Institute in Canada, and the EC in Turin, Italy. And you are also consulting for the World Economic Forum on the future of computing. And you are author of 4 textbooks and 2 popular books that we can find in Singapore. Probably you know that. So it's Decoding Reality and from micro to macro. So with this, Vlatko, welcome, and the floor is yours.
Thank you very much, David. I'm very happy to be talking to you, and especially on the topic that you asked me to talk on, which I think is a very interesting one. I will explain, of course, the Aharonov-Bohm effect. First of all, I think most people may be familiar. I will dedicate maybe one slide just to explaining the basics. And then, of course, what I have to explain is what I mean by a classical and what I mean by a local account of the Aharonov-Bohm. So these both words have a very well-defined meaning. And it's interesting. The reason why this is interesting is because you will frequently read certain claims that somehow in quantum mechanics, we are forced to use the vector potential of the electromagnetic vector potential instead of the electromagnetic field. In this case, it would be the magnetic field. And that's in order to preserve the locality of the whole account. And it's interesting that actually, if you think about it a little bit more carefully, you will realize that the same story really goes through classically, and that's basically what I want to tell you about. It's a very simple account, and it's somehow maybe a historical accident that we came up with the explanation the way we did after quantum mechanics, of course. It could have happened differently, and I think David noticed a paper of mine on arXiv where I basically gave a kind of classical account and even rewrote history in this case. So basically, the Aharonov-Bohm effect, I think everyone probably will know all of these things, is that you have an electron. I hope you can see my cursor here, that you have an electron coming into an interferometer. you know, it looks a bit like the Mach-Zehnder interferometer. You have a beam splitter. At some point, somehow you split your electron, and it takes two different routes around a magnetic flux, which is as tightly confined to a small region as possible. So what you're trying to achieve with this, usually you have some kind of coil, which is in the direction that's perpendicular to the slide here. And of course, if the coil is really in the infinite limit, when the coil is infinitely long, you can actually make the external magnetic field zero. So there is no magnetic field anywhere where the electron is present, if you like, and it's all confined into this small region. And then the interesting thing is that despite the fact that the magnetic field is zero, this is why this is sometimes used as an argument for the vector potential. You still, when you close this interferometer, so it's really like a Mach-Zehnder, you split the electron, you let the electron encircle the magnetic flux in both directions at the same time, then you recombine these two parts, you re-interfere them, and then you measure a phase. And the phase can be written in two different ways. And one way is simply the integral around this closed loop of the vector potential, which basically is really this argument that even though the field is zero wherever the electron is, you can now use the vector potential, in fact, to calculate this. However, if you use the Stokes theorem, and I think most of you again will know, this is a very famous maneuver in physics that we use from mathematics very frequently, you can actually convert this into a flux integral of the magnetic field. But the flux only exists in this very small, tightly confined region. So that's when Aharonov and Bohm wrote this paper, which I'm citing here, and I'm citing my work with Chiara, if you want, as the latest fully quantum account of this. But when they wrote this, they kind of noted that actually it looks like the phase is picked up in a non-local fashion. Non-local in the sense that it seems that the phase can be seen as a function of the magnetic field, but the magnetic field exists far away from where all the action, if you like, takes place. So it looks almost paradoxical. And many people would even now say that this phase is non-local in nature. And what I want to say is the exact opposite, actually. I want to tell you that there is a perfectly reasonable local account of this. And in fact, it can be even explained classically in a way that I will explain in a little bit what I mean by classical here, because it's not entirely clear. I'm abusing maybe the word classical a little bit, but I think this is usually how we think about it in quantum mechanics. So let me say it now, and you will see what I have in mind. And there is, when you treat fields in quantum mechanics, you have this very confusing language where you say, I go from first quantization, and the first quantization, we think something like the Schrodinger equation or the Dirac equation, even if you want to be relativistic, or Klein-Gordon equation, any of these will do the job for us, because actually in this case, the electrons are really completely non-relativistic. So it doesn't really matter. The Schrodinger equation will do the job, if you like. But then when you do a field theory, you say, oh, now I'm actually going to quantize the wave function that I get from this Schrodinger equation. And I'm going to think of this wave function as a field. And the reason why we do this, it sounds weird, you know, why should I second quantize? And of course, you immediately think, why not third quantize? You know, what would that mean? And so on. And I think this is possible to explore. But second quantization simply means that you are acknowledging that you can create and annihilate particles in this field. So if you're thinking of an electron in the first quantized regime, Now, when you second quantize, you are allowing many electrons to exist in your field. You can create them, annihilate them through some processes, and so on. That's really what second quantization means. But it sounds a bit weird. When you ask yourself, what about photons? What about the Maxwell field? What about, you know, the electromagnetic field? Then somehow, confusingly, you go straight from the classical description to the second quantization. There's no first quantization, as it were. If you want to compare these things equally, and that's what I'm saying on this slide, you could actually, and many people advocate this view, you could think of Maxwell's equations as the first quantized picture. You can think of the combination of the electric and the magnetic field as a kind of wave function for a single photon. So you could formally say, let me take Maxwell's equations, they are classical, but they also fully apply to a single quantum. I can think of them as the Schrodinger. You can even rewrite it so that actually it really looks like the kind of Klein-Gordon equation, in fact, in this case, because it's relativistic. And that would be also your first quantization, if you want to compare the electrons, if you like, and the photons on an equal footing. So that's what I'm going to be assuming here. I'm going to be saying, if you think of the Maxwell's equations as classical, which is how we think of it, then if you talk about the same level of description, you could think of the Schrodinger equation as also the classical description, which we then have to quantize in order to get the quantum field theory. So in that sense, it seems to me that that's the way I wrote my paper, in fact, is to imagine a civilization somewhere on Mars, you know, aliens, which actually discovered the electron field. They discovered the field through interference, various interference phenomena, before they discovered the individual electrons. So I was trying to make it logically consistent with the electromagnetic field, where, of course, people understood from the days of maybe Huygens, even should be the person credited. Huygens was arguing that that light should be treated as a wave. And from those days, people already understood somehow, of course, with Faraday and Maxwell, we have the full field description. People understood that the electromagnetic field should be treated as a field, as a wave. However, it took almost another 50, 60 years for people to advocate that this field actually consists of individual particles, of photons. And you know that it was the famous Einstein 1905 paper that really argued convincingly for the existence of photons. And even later, of course, people doubted this for a long time until we really conclusively developed all sorts of tomographic methods. And of course, now it's beyond doubt that photons exist. So I'm kind of imagining this civilization which can do interference experiments with the electron field, but they don't get the single clicks from the individual electrons in the same way as they get interference phenomena from optics, but they don't really know that there are individual photons in this field. And that's what I mean by classical. Otherwise, it's really very difficult to think about what it would mean to be classical in this context. Now, let me tell you a little bit how a field would behave in an interferometer. First, I will describe an interferometer in general. I will tell you this maybe with optics in mind. But of course, I just want to reinforce this idea that having Maxwell's equations describe your interference, or having a single photon description with a quantum equation, if you like, with a Klein-Gordon, or in this case, you can do some kind of Schrodinger-like treatment, it's completely equivalent at that level. So it doesn't really, you don't have to acknowledge the existence of individual photons if all you want to explain are the interference fringes when you repeat the experiment many times. So let me show you how this goes, and then I will immediately apply it to the Aharonov-Bohm effect. And the key thing now I want to emphasize is the locality of our description. And I will explain to you exactly what I mean by this. I think this Mach Zehnder is a perfect, I mean, you know that this is probably the favorite qubit of everyone's in quantum information. And I think it's a really, it's a nice, of course, it applies to any form of interference, but I think this one in particular is the best one for what we have in mind. So here is light coming in. Again, could be a single photon, could be a classical laser pulse, if you like. It really makes no difference at this level. It splits here. Then in one arm, you introduce a phase shifter. You know, there is a medium, some kind of dielectric medium, through which when the light propagates, it picks up an extra phase shift. And then when these two beams recombine, you get the usual probabilities for the beam to come out one way and the other one, which are the sine squared and cos squared of this phase that was inserted. Now, what I mean by local is that the phase really was put in one arm of the interferometer. It's introduced exactly in one of the two parts of the interferometer, and it's not introduced in the other one. It could have been introduced in the other one physically, and it would give you the same result. But in this case, it really exists in the upper arm, and that's exactly where it interacts with either classical field, if you want to think about it like that, or the single photon that goes through the phase shifter. Here now at the bottom, I want to show you why in quantum mechanics we are sometimes confused, but this is a misconception. We are sometimes confused by this, and we say, or some people say, not everyone says this, some people say that this effect is non-local. And it looks non-local because if you, now I'm doing a quantum description, and I will switch back to classical on the next slide, if you like. In fact, it will be both quantum and classical. That's the beauty of this. Here, if you think in terms of the wave function, the Schrodinger description, if you think of 0 as the vacuum and 1 as one photon, then the state after the beam splitter is actually, looks like an entangled state. It's 0, 1 plus 1, 0, meaning the photon is not here, it's here, and vice versa in a coherent superposition. And now if you introduce the phase in one of the two arms, which I'm deliberately writing in this funny looking way, that the phase pertains to the photon being in this arm here, the property, this is simply linear algebra and tensor products in mathematics, if you like. It looks as though the phase could be moved into the other mode, into the other arm of the photon. So suddenly, this is something, by the way, that the practitioners in quantum computing call the phase kickback. So somehow I'm kicking the phase in one side of the interferometer, and suddenly it pops up on the other side of the interferometer. This is what Schrodinger, by the way, called steering. Schrodinger already understood that this is a consequence somehow of entanglement. And also it looks like it could be a minus phase, which is completely irrelevant. You will get the same probabilities, of course. So I'm writing this kind of phase kickback in 4 different ways. And I'm saying because of the way we describe states in quantum mechanics, they all look the same. And some people you will hear say, oh, that means the phase is non-local because I kick it in one arm, but it looks like I could describe it as being introduced in a completely different arm that's far, far away from this arm. And this is really misleading, and it's simply a property of the wave functions, like I said, but it's nothing to do with what really is happening in practice, because obviously in practice we know exactly where the phase was introduced, and the interaction that was physically relevant, and I will comment on that in a second, really was all taking place inside where the dielectric medium is. It's all local, namely the photon couples to the medium at the point where the two exist simultaneously, if you like. There's no action at the distance whatsoever in this case. Now, the Schrodinger picture is confusing in this respect. However, if you look at it as a field, and maybe that's always the best description if you want to preserve locality, of course. So now I'm doing a completely field description, and it could be either quantum or classical. That's the beauty of this now. So what am I doing here? I'm taking the electric field. You could think of A and A dagger either as the complex numbers, meaning a complex number and the conjugate, which gives you a real number. This is how we would describe the electric field if we were using Maxwell's equations, if you like. Or you can think of this as annihilation and creation operators in quantum mechanics, and it's exactly the same description. So like I said, when you are talking at the level of a single photon, it's indistinguishable how we describe this from a classical pulse. It's the same description, really. It will not change. Whether these are complex numbers or operators, if you like, in quantum mechanics, you will get exactly the same outcome at this level. So here is the electric field in the left arm of the interferometer, and I'm putting a comma to separate the two modes. Here is the electric field in the right arm of the interferometer. This is before the phase was kicked in, after the first beam splitter. Then I kick the phase in, and you see, if you follow the field, it's much clearer what's going on, because when I kick the phase in, I kick it in only on the left. Nothing happens to the electric field on the right-hand side. It exactly stays the same. The field description is designed to preserve locality of this interaction. That's precisely why Faraday, and of course later Maxwell, mathematically speaking, advocated the use of the field to avoid any funny-looking action at the distance. Then you do the second beam splitter, and it's only when the two modes mix that you now get the phase to cross from one mode to the other mode. So this happens right here at the place of the last beam splitter, and the last two output arms are these two arms. So you can see that the field description makes absolutely no mistake about where the phase is. The phase is exactly where it's meant to be, where the phase shifter is. And only the final mixing, the interaction between the two modes, puts it into both of these arms. And the rest is now very simple in my description, because all I need to do really is calculate the expected value of the output statistics of the two output ports of the final beam splitter. And of course, you will get the cos squared and the sine squared probabilities that you normally get. So absolutely the same result, no surprise there. But I actually went deliberately with fields, or with operators, if you like, simply to demonstrate how locality is preserved here. And there is, there is nothing mysterious quantumly there, other than, like I said, you will now have to treat A and A star, if you like, as annihilation and creation operators of the electromagnetic field. Of course, the story is different, and many of you will know if you now engage two photons, because you will have to take into account the fact that they bunch. And the bunching effect obviously is something that is not part of any classical description. That's not really something we can capture there. But at the level of a single photon, the descriptions are completely identical. And now I want to give you a little bit more of details how you would do this, actually, mathematically speaking. But I want to keep making the analogy between optics and matter wave interferometry, which is what the electron does in the Aharonov-Bohm effect. Again, this slide is all about de Broglie. de Broglie's ideas are the key here, as you know. And the top interferometer is the light interferometer. And I just want to tell you, the way we simply explain this phase shift in one arm is the usual e to the I kx component of your phase, k being the wave number and x being simply the optical path length of this. And the phase is the relative phase between the two paths, which translates itself into the relative, into the difference between the wave numbers in the two arms. I'm sorry, yeah, here we go, which actually ultimately is the difference between the refractive indices in the two arms. In one arm, you can think of that this propagates through the air, the refractive index is 1 on the order of 1. In the other arm, we're talking about some dielectric medium, and the refractive index is whatever it is. It could be greater than 1. It's between 1 and 2, let's say. And basically, this is exactly the relative phase that gets detected in the final probabilities. This is how we would describe this optically. Now, the interesting thing is that if you reverse the role of matter and light, you will get the Aharonov-Bohm effect. So that's the beauty of this. And even more interestingly, we call this effect the Aharonov-Bohm effect, but actually it was first introduced by Ehrenberg and Seidel some almost 10 years before Aharonov and Bohm. This is this paper I'm citing here, which exactly starts to advocate matter wave description of electron interference as it propagates through a non-trivial medium. Non-trivial meaning that the refractive index is not equal to 1. So how would you describe the experiment with an electron going through these things? You would say the following, and what is it that creates the non-trivial refractive index? It's the vector potential. And that's the key thing here. So even if you go classical description of this, and you really want to talk about these matter waves as being described by some classical wave equation, and that's what I'm advocating, that you can think of the Schrodinger equation or the Dirac-Klein-Gordon, whichever one you want to use, but Schrodinger is sufficient because it's non-relativistic. You can actually think of these waves as propagating in different refractive indices because this vector potential is the entity that determines the refractive index. And it must be the vector potential. It cannot be the electromagnetic field. That's the key thing here. So even if you follow a completely classical treatment, I'm doing a completely analogous classical treatment of this, you are already forced into coupling your electron, if you like, your electrons in this case, as you repeat the experiment, to the vector potential. And it simply says this: in one region where the electron is, there is one vector potential, which gives you one kind of refractive index. In the other, there is a different refractive index. And the difference between the two is exactly what ultimately gives you the Aharonov-Bohm phase shift. And of course, this entity here, the difference between vector potentials times the charge of the electron, is what you have to ultimately integrate around the closed loop in their experiment to get the phase. And that's really interesting. But now I want to come back to the locality issue, which is also interesting here. If you, for instance, look at the interferometer here, and you say, wait a second, if I didn't put the second beam splitter, and I kind of look at the experiment here, just after the phase shift, could I talk about the relative phase difference between these two arms? And the answer is yes, of course. That's exactly the point. There is a relative phase between the two arms, and I will calculate it on the next slide, which is well defined anywhere along this interferometer. At any point locally, you can define this relative phase. Relative phase is something, of course, that we measure And one way to measure this is disclosure through the beam splitter. But you can do this in principle, at least, in different ways. And that's what I would like to advocate now, that if we could extract this phase locally, we could even demonstrate more conclusively that this really is a completely local description. Let me get to that mathematically now, because there is a subtle issue of gauges here. And that, I think, is what leads to many debates on this matter. So here is the electron coming in. Here at x0, it gets split. It goes one way around the flux, it goes the other way. And then before I close the beam splitter with the second beam splitter to get the fringes, if you like, to get the probabilities, I will now ask the question of what is the relative phase between these two. And some people would say, wait a second, if you're talking about the vector potential, that's a gauge dependent entity. I can change the gauge and I will then change the vector potential. So how can you tell that this phase here, the relative phase, is actually invariant under this? And actually it is invariant. That's the beauty of this. And a simple way of doing it is really to calculate. I'm calculating the integral of the vector potential along this path minus, because the relative phase, minus the vector potential along that path. And if you look at it, when you change the gauge, remember, changing the gauge in electromagnetism simply means adding a gradient of some potential theta. I'm calling it theta here. Then you will actually get the new phase difference, which is the same as the old difference of the vector potential, plus this difference of theta of your gauge, if you like, added gauge at x1 minus the gauge at x2. And this is something that in the quantum description, we add to the wave function when we change the gauge. So actually, because the wave function changes simultaneously, this difference between the gauges also disappears. It's something that cannot be detected. And so that's very interesting, that the difference between the phases, wherever you stop this, you don't have to close the loop, if you like. Wherever you stop this experiment, the difference between these two values is actually an absolute quantity, if you like. It's independent of how you choose to describe this. There's a very nice account of this by Keith Kasunik. This is this second reference. I'm citing my paper that David noticed, and I think this is what prompted this invitation. But if you want to read a slightly different, but along the same lines account, then this second paper in the American Journal of Physics is highly recommended, because it's really a very beautiful, very simple, almost first, second year undergraduate treatment of this. Now, what I want to do is I want to make one more comment before I tell you the difficulties. So here I was using the wave function just because it's maybe familiar to most of us, but you can do this gauge thing, of course, with classical fields, and you would get exactly the same result. But there is a nice, and I will make a slight digression in a minute. Here is the most formal way of doing this, if you like. And to my surprise, Schrodinger was the person who actually has a Nature paper, I think in 1952, where he, nothing to do with the Aharonov-Bohm effect. This was before the Aharonov-Bohm effect. He wasn't aware of the Ehrenberg and Seidel paper either that I cited before. What he basically wanted to do is give a realistic account of how electrons couple to the electromagnetic field. He wanted to talk about electrodynamics, but in a kind of realistic way, without complex numbers. And so he was advocating defining a new vector potential, the A bar. Mu is just the index 0, 1, 2, 3, which goes for the temporal and the three spatial components. He would say, if you define the vector potential as the old vector potential plus a function, psi is your wave function of the matter. In this case, because he wanted to describe electrons properly, he was using a complex field, as people do. Not a scalar one, but a scalar, but a scalar complex field. So in this case, this psi is a complex function, if you like. But actually, he was advocating to add the electronic description. This bit here, the addition, is exactly your Aharonov-Bohm phase contribution, as it happens, actually. And then he said, I can define a real electron field phi. This is what I was imagining my aliens would be using. They would be using phi before they discovered the full quantum nature and the existence of individual electrons. And that's the modulus of the complex field. And then if you introduce this kick, extra kick, into the old vector potential, you will actually have a realistic description, if you like. These are real functions of how the electromagnetic field described through this A bar couples to phi, which is the real description of the electron field. And the coupling is the usual coupling that we are used to in electrodynamics. So there is a source term here that determines how the field couples to it, and then you have the usual Klein-Gordon equation for the field, and you have this electromagnetic contribution on the other side. And if you work through these equations, you can actually describe any situation, but in particular, you can describe the Aharonov-Bohm effect in very simple terms. And that's exactly what I did in my paper. But remember, the price to pay is that you are thinking of the Klein-Gordon field not as a quantum field, but you are thinking of it as a classical field, which if you want to make into quantum, you have to upgrade these fields into operators, which is again what I said we would confusingly call second quantization, but in this case there is no first quantization. I'm just calling it a classical field to start with. So basically, electromagnetic field and the fermionic electron field are treated completely on an equal footing here. And so this is this digression that I want to make one kind of final point. And then I want to tell you what I think is the key difficulty in confirming this locality, because I think this could be an interesting experiment. And then I will stop there. And I hope that you will have some questions and we can discuss this. I'm sorry about the busyness of this slide. I did some cut and pasting from my quantum optics textbook. Actually, this is the standard argument, how in gauge theories, gauge field theories, we try to argue for the electromagnetic field. In fact, any field can be derived in this way. This is exactly, by the way, how we do the standard model. It's all about really gauge fields. So the argument goes like this. I just want to show you that actually it's very strongly connected, of course, to what we've been discussing now. Here is the Schrodinger equation. You know, here is the kinetic term, here is the V, is the potential, if you have any potential there, the wave function, and then that equals to the to the energy operator, IH bar d by dt, the wave function. Now, the gauge argument says the following. Imagine I want to change my wave function by some phase, which is a function of x and t. So if the phase is not a function of space and time, then your Schrodinger equation is invariant under this change, because the phase just pops out and you can cancel it on both sides of the equation. But if the phase is dependent on space and time, then the derivatives, this is the second derivative in space, the first derivative in time, if you like, you will actually also have to differentiate the phase. And it will give you two extra terms. And if you want to preserve the Schrodinger equation, of course, the Schrodinger equation is now no longer preserved under this change. But if you want to preserve it, then you should add a contribution to your Bell operator, to your momentum, which is actually a gradient of that phase theta, and you should change your potential with the old potential minus the temporal derivative of your phase theta. That's how you're going to end up canceling these derivatives, and you will go back to the old Schrodinger equation. So that's interesting, because if you turn the argument around, and if you say, I want my Schrodinger equation or the Klein-Gordon equation, people usually do this with Lagrangians in general. Maybe you've seen this more with Lagrangians in quantum field theory. But if you want to make your field description invariant under the phase kick, which is space-time dependent, then you need to introduce something that looks remarkably like the electromagnetic vector potential. So somehow light, if you can argue that the electromagnetic field exists in order to preserve the gauge, the phase, in this case, invariance of our material description of the material field. That's the usual way how these gauges work. And by making this phase into an operator, a 2x2 matrix, 3x3 matrix, you can actually take into account the weak forces, the strong forces. You can even do gravity this way, actually. And that's my next slide, because some of you may be wondering, could I do the same Aharonov-Bohm logic in the gravitational field? And I don't want to spend too much time. This is even more controversial in some sense, but there is a beautiful experiment, recent one, a few weeks ago, published in Science by Mark Kasevich and his team, which is actually testing the gravitational Aharonov-Bohm effect. I don't want to describe, it's a beautiful experiment actually, but all I want to remain at the very kind of superficial mathematical level. But all I want to say is that if your vector potential now is the metric of the gravitational field, you know, the gravitational field is described by this G mu nu, a 4x4 matrix really, which describes all the metric components. And this thing here is just a weak gravitational field contribution to that. You can think of this G mu nu as analogous in gravity to the vector potential. And if you use these kind of values for gravity in place where I was using the electromagnetic potential, you will actually get the gravitational analog of the Aharonov-Bohm effect. And you would get exactly the same result. It's all to do with the potential differences in the gravitational field, the potential difference between in this, I think in that case was a rubidium beam of atoms that was split, and then one of these arms of the interferometer went in a different gravitational field to the other one, and then they were recombined, and the output was measured in exactly the same way. It's a kind of fancy Mach-Zehnder interferometer, and you could detect the phase difference, which is the potential difference in the gravitational field. Very beautiful experiment. Now I want to finish by of course, the question is, you know, what is the big deal then? You know, why is this discussed so much? What is the problem there really? And the key problem, and this is where quantum mechanics makes our life more difficult. So of course there is a quantum mechanical thing. So the description goes through beautifully classically. But if you want to demonstrate the locality conclusively, I think this is something that David and I have discussed in the past actually, because he's done a lot of work on geometrical phases and related issues. And I think here the key issue, and there is a lot of literature on this, would be to really demonstrate that there is a phase difference between these two arms without closing the interferometer. Could you really establish by some local tomography, that's the key word here, could you do some local tomography so that you don't have to recombine? Because you see, the problem is when you recombine these two beams, then your integral of the vector potential becomes the flux of the magnetic field. And then suddenly everyone says, oh, it's the magnetic field doing all the work, and therefore it's non-local. That's what gives you the phase. And we want to counter this argument by saying it's not, it's really to do fundamentally with the potential difference. It's all to do with the vector potential. And basically, that's why we don't want to recombine the two beams, if possible. We want to really do some kind of local tomography in order to do that. By the way, in gravity, they try to do the same thing. They try to say that there is a potential gravitational difference. However, there is no gravitational force, there's no gradient of the gravitational field along either of the two paths of this rubidium cold atom gas, if you like. So basically, in that sense, we can really do this kind of treatment with any field, where you say the field itself vanishes along the paths that interfere, but the potential that generates the field actually exists. And this is what we are ultimately measuring. Now, what is the difficulty there? The difficulty really is that even though we claim that we have a classical description, ultimately we are really interfering individual electrons. And that's causing us problems. And the reason is the following one. What we really want to claim, it's exactly what I was saying with the photon, but now I'm going to say it with an electron or with an atom, with a material object, if you like, is we want to say that when you have an electron, let's say in a superposition of two different places, you want to think of this as an entangled state, 0, 1 plus 1, 0. Or it could be n atoms in one potential well, n plus 1 in the other, plus vice versa. This would be maybe some kind of a description of the state of the superconducting qubit, for instance, where you have different number of Cooper pairs on the two islands. Now, if you want to measure this just locally, if you want to confirm that this state is entangled, if you want to extract the relative phase in this superposition, if you like, then what you really need to be able to do locally is you need to be able to make local measurements here and local measurements over here to try to extract the phase. And this leads us to this superposition of different numbers of particles. You have to be able to superpose the vacuum, let's say 0 plus 1 particle. And that's something that we cannot do with electrons. That's actually what makes our life difficult here. So people are happy to acknowledge that you can superpose one vacuum state of the electromagnetic field plus one photon. But if you're talking about the corresponding superpositions of 1 electron plus 2 electrons, or 0 electrons plus 1 electrons, then we have super selection rules that go against this. And that's actually the last thing I want to comment on before I offer you one solution that I think works. It's a kind of trickier experiment, but I think it would do the job for us. So let me briefly tell you why there is a super selection rule. This is an argument, I think, related to Wigner. I don't think Wigner did a lot of work on super selection rules. I think I've maybe slightly upgraded this argument to suit someone in quantum information. I don't think Wigner would have written it like this, because Wigner wasn't into local operations and classical communication and things like that. So that's what I'm doing here. I'm saying, imagine I have Alice and Bob. I want to show you why, if you could make a superposition of no electron plus 1 electron, you would actually be able to signal faster than the speed of light. And that's why you cannot superpose even an odd numbers of fermions. It's a general argument for fermions. So here is basically the vacuum state for Alice. And imagine that Bob could create a superposition of no electron plus one electron. Now imagine if instead of Alice having the vacuum, she creates one electron instead. What is interesting is that because of the anti-commutativity of the fermionic operators, when you swap the fermionic operators, when you swap the mode 1 and mode 2 operators, you get a minus sign, you get a pi phase shift. This is the Pauli exclusion principle, if you like, the fermionic statistics. What now happens suddenly is that Bob's state becomes an orthogonal state, 0, -1. So if Bob could create a superposition of the vacuum and one electron, he could instantaneously tell whether Alice didn't do anything or Alice created one electron in her own side, in her own mode. So this would be an instantaneous change. And of course, this kind of instantaneous change is ruled out by relativity. No one wants to have this in any field theory, like I said, which led Wigner and many other people. There are all sorts of arguments that were made more and more formal by various physicists, which would say this is why we cannot, this is the so-called parity superselection. You cannot have, you can have even and even numbers. You can have 0 electron plus 2 electrons plus 4 electrons. This is basically your BCS superconducting state, but you cannot have 1 electron plus 2 electrons or 2 plus 3. It's just impossible, relativistically speaking. And this is kind of the argument that we have. Now, how do we overcome that? And this is the last thing I really want to say, and then I'm going to go to conclusions. The way I would do this, really, and there's just one way, I'm hoping there are maybe many different ways of doing this, is unfortunately, we have to use 2 electrons, like I said, simply because we cannot create superpositions of 0 plus 1 electrons. But we could create superpositions of an electron being in one mode and an electron being in another mode. This is just a simple superposition of a single electron across 2 different modes. So imagine that you set up the experiment in the way that you don't have any magnetic field at the beginning, and all you do is you create a superposition of a single electron. This is your reference state, if you like. This one is not the one that I want to pick up the phase, the Aharonov-Bohm phase, but I want to use this as a reference against which I will confirm the phase of the other one. Then I will switch on the magnetic field, introduce the second electron pair, which then picks up this phase locally in each branch. As it goes along, it gets this phase, which you can think of as a refractive index due to the vector potential. And then I stop the experiment. I don't want to close the interference. What I do want to do now is I want to jointly measure the 2 electrons on one side and on the other side in order to extract this relative phase. So mathematically speaking, I have one pair, if you like, of modes that are entangled, but single electron across 2 modes without the phase. And then I have this electron that actually did the journey after the magnetic field was switched on. And here is the Aharonov-Bohm phase. And I claim this phase exists even at any point of this interferometer. It's picked up locally, the phase difference. And now, why can we measure this phase? Because we have 2 electrons now, and we can locally measure in the basis 0, 1, plus or minus 1, 0. So that means the electron is here and it's not over here, if you like, plus vice versa. I'm working in the subspace of a single electron here and the subspace of a single electron on the other side. So now I can really think of this as an entangled state. And what I really want to determine is what kind of relative phase I have between these 2 elements in the superposition. And the claim here, at least in this thought experiment, no one has done this experiment, but I think it would be a very interesting experiment to do. At least in this thought experiment, you don't need to close the loop at all. You can do this kind of local tomography to actually uncover the phase without, you know, engaging the full description of the closed loop that then involves the magnetic field invariably. So then it's really impossible to argue that it's really the vector potential that somehow leads to this kind of description. So I'm going to leave you with this. I have a few other thoughts there that we can discuss, and maybe if they arise in our discussion, but let me just briefly summarize the main points. I appreciate that this could be confusing for some of you if you've never seen this kind of arguments before, but the main point here is that both quantum and classical fields can be made, I'm not saying they are in every description, but they can be made to be perfectly local in every phenomenon that we choose to describe. And local simply means that when you couple two fields, they couple at the point of interaction. So the electron field at X couples to the electromagnetic field exactly at the point X, not at a different point X prime. This we would call non-local. And in no experiment that we've done so far, do we ever get any evidence that anything is non-local. So all of our descriptions, in fact, are completely local in this way. And I'm saying this is true no matter how you treat this, but the point I made is that sometimes when you follow the Schrodinger picture, because of the wave function, because of the way that we do mathematics with the wave function, you may be misled to think that some kind of quantum phases are really non-local. But if you want to demonstrate locality beyond any reasonable doubt, then you should really just work in the Heisenberg picture. And of course, quantum field theory is exactly designed in the Heisenberg picture, precisely because we take classical fields and we upgrade them to operators. And this naturally gives you the dynamics of the corresponding operators. The vector potentials, the electric, the magnetic field, anything can be described this way. The point I made about the Aharonov-Bohm being classical, that you can do a classical account, requires, and this is the key thing, requires us to think of the Schrodinger equation or the Klein-Gordon equation or the Dirac equation, maybe more appropriately because it's an electron. We should think of that as a classical wave, really. Something we haven't yet quantized to make it into the proper quantum mechanical field. So if you want to use Maxwell's field for the electromagnetic description, then you should use the corresponding, let's say, Klein-Gordon field to describe material fields. And if you do it at that level, you could actually think of this as a fully classical description. The last question I just want to leave you with, and then I will stop, is can you really, so there was one phenomenon that I sneaked in here when I was talking about the super selection rules, which was the phase that's acquired when you swap two fermions. And the question I want to ask, and I think this also is a very interesting direction, is could you think of even the particle statistics phase in a local way? Could there be a field description of how the exchange phase is actually acquired in quantum mechanics? I think this is a fascinating, so you can see that I'm going in the direction of militantly making everything local in this point interaction way. And I think it would be amazing to see, to even discover that possibly even the fermionic phase can be done in this way. I want to thank you all for listening and for your attention, and I hope that there are many questions. Thank you very much.
Thank you, Vlatko, for this very exciting talk. Yeah, so who wants to ask the first questions? Okay, so I will ask the first question then, Vlatko. So yeah, I understand. I mean, so what you want to do somehow is to measure the phase. I mean, without closing the interferometer, in order to have this local interpretation. I mean, so there is a way to do it somehow. I mean, instead of using elementary particles like electrons, you can imagine to have a composite system like an atom, and you know that we can create, I mean, artificial gauge field with this atom, right?
Yes.
And one of the interesting aspects of this artificial gauge field is that they are act only on some specific states of the atom. So you can imagine to have a situation where you create a coherent superposition of two states in the atom.
Yes.
For example, you take a clock transition, and one of those states are subject to some artificial gauge field. So you will pick up a phase, a geometrical phase, and then after that, since you have a coherent superposition, somehow you can also close the internal interferometer somehow,
yes.
Okay, without closing spatially. I mean, is it something that you will be happy with? Or?
I think so. I think I would be very happy with that. I mean, the only thing, as you said, this is probably more like a simulation of sorts, because you're doing simulated gauge fields. But I think this would be great to do, because also I think the key thing is what you mentioned, not to close the interferometric loop. I think this would be a fantastic proof of principle simulation to do, if you think it's feasible.
I think it could be feasible.
That would be great. Yeah, I'd love to talk more about this. I think
sure.
This is a great point, actually.
Okay. I have another question also. I mean, you were talking about, I mean, go beyond somehow the U1 symmetry of electromagnetism.
Yes.
I mean, so you talk about, I mean, neutrino or whatsoever, SU2, SU3.
That's it.
Yes. So what does it bring more in this business if you go to higher scale?
Oh, good question. I think in terms of, that's a very good point as well. In terms of locality, I don't think it changes the story, because this phase, even though it's a more complex object now, it's still defined at every point, just like a field. The only additional element is that the different phases now no longer commute. Now, of course, it matters which phase you kick in first and which phase you kick in second, which I think is a little bit like in the experiment that you have in mind. You can also have some kind of possibly non-commutative behavior, if I'm right. Is that possible to do?
Yeah, sure. I mean, it's possible to do, but if it's non-commutating, I mean, so imagine you have a spinner, right? And then, so if you apply a non-abelian gauge field on the spinner, that's what we do in our lab. So what you do is not on. I mean, you can rotate the spin.
Yes.
Okay. You can rotate the spin. So this rotation, you can see it somehow.
Yes.
You can already claim that it's a local measurement.
Yes.
Right. You don't need.
Yes, you're right. Exactly. So I think these things, exactly as you said, they are frequently in quantum computation used as gates, right? Because you can now rotate in this subspace, relevant subspace. Yes, you are right. So it's no longer a phase, really.
It's not longer a phase.
Yes, that's right. But
the first experiment I have in mind is really.
It's just a phase. I understand. Maybe both could be done. Both would be interesting to do, actually. Even the second one, I think.
Okay.
Yeah.
Okay. Other questions?
Thanks so much for your very interesting talk. So I would like to ask, so now I understand the local in your context is that every theory can be written in a local theory. The interactions only happens locally. So now I understand this, but I would like to understand, I mean, the AB effect, the non-local AB effect. What is the fundamental misunderstanding of this non-local word?
Yes, it's a good question there, because sometimes it's I think the main way in which it's phrased is really that we should only think of the electric and the magnetic field as ever being able to affect anything in electrodynamics. And so some people would say those are the only elements of the field that should have reality, so to speak, attached to them. Reality in the sense, you know, if you put a test charge, they will be able to kick this test charge. If you want to think of the Aharonov, and that comes to then of course Aharonov and Bohm make exactly this point. They say if you want to think of the electric and the magnetic field as the only real entities, then this kind of experiment with an electron interfering is very weird, because the path of the electron never goes through a non-zero either electric or magnetic field. So then you have it seems you have a difficulty explaining how can you locally acquire a phase when locally along the trajectory the field itself, the B field, if you like, in this case, that's the relevant one, perfectly vanishes everywhere. And of course, their answer would be either, I mean, I think it's not even clear that two of them agreed on this, by the way. So I think because many things have been written on the phenomenon even afterwards. One way to put it is to say, well, that means that this phase is genuinely non-local. It's done by the magnetic field at a distance. And I'm arguing against this. I don't think this is true. We really don't need to do that at all. This is just this is unwarranted in this case. However, another way to put it, and I think Feynman has a very nice discussion of this in his lecture notes. Another way to put it is that you simply have to acknowledge that the vector potential now plays a fundamental role, and therefore is also real if you want to think of reality as it can affect things. And I think to me the message would be more this, that at this level of description, if you really want to preserve local point-by-point interaction, you can only do this with a vector potential. And that's interesting. That's just generally true for any field that we know. I'm not aware of any general proof that this has to be like this always. This would be fantastic to be able to give even a general argument. But I think in all particular cases that we have, we always have to go through the vector potential. And it's true quantumly, but it's also true classically. Maybe the easiest way to see is just to do the classical Hamiltonian treatment of this. And again, the vector potential comes in straight into the description there as well.
Oh, actually, in light of this, I would like to ask something else. So basically, sometimes people do some external fields like perturbation theory, and there are two ways of introducing these perturbations, like introducing by using magnetic and electric field, or by introducing a vector potential. But do you think which one is ultimately the correct one, or there always be equivalent, or there could be some tricky cases that one of them could be incorrect?
Probably it's a good point. The safest way from our discussion would really be always to start with the vector potential, and then all of the other fields are really derivatives of this. Then you just derive your vector potential in the appropriate way, and you can generate all of the field components. of course, the vector potential, the subtlety there, as I said, is that the vector potential is not gauge invariant. There is a practical issue there, in the sense that, like I said, the gauge invariance is simply seen when you talk about the relative phase. So even though it is not gauge invariant, the relative value is always gauge invariant. So we have no problems there at all to account for all of this. Maybe there is a practical consequence there, which is to say that some gauges are simply more natural than others. They are easier to demonstrate certain things, and that's maybe what should govern your choice of the gauge. But ultimately, really, it makes no difference. For instance, because I keep emphasizing locality, and you know, we're really trying to preserve relativistic treatment here. We don't want to violate. We don't want to get into trouble with relativity, really. Because of that, I, for instance, like the Lorentz gauge a lot. The Lorentz gauge, of course, is immediately relativistic. However, it may confuse you as far as certain other things are concerned, which you then have to address later. So, you know, Lorentz gauge is good for some things. However, it could be, you know, more cumbersome than the Coulomb gauge, which I think most people would use for certain other scenarios. The bottom line is that it really doesn't matter, that one of them may be easier than the other, but because we are always talking about relative phases between different points where we're describing the field, any gauge will do as well as any other. And then you can derive from the vector potential all the other relevant fields, and of course they are completely gauge independent.
Okay, thank you so much.
Thanks.
Okay, do we have other questions? Okay, so if it's not, Vlatko, thank you very much.
Thanks a lot.
Talks, and all the best for the rest.
Thank you very much, and hopefully we can talk more about your suggestion. Sounds to me really like a great experiment.
Okay, sure, Vlatko,
Yeah.
no problem.
Okay,
Bye-bye.
take care. Yeah, bye-bye. Take care.
Bye-bye.